Thanks so much, Anton. Thank you for the introduction. I want to thank the organizers of the conference for the invitation to speak to you today. And my job is to tell you about some project that has started maybe a year and a half ago and has really blossomed recently. It's a project about the Benjamin-Ono equation. And in this particular talk, I want to focus on the so-called zero dispersion limit of this equation. And the work that I'm about to discuss is supported by the National Science Foundation. It's joint work with Elliot Blackstone, who recently finished a postdoctoral position at the University of Michigan. Okay. And Gasso from the University of Rennes, Patrick Girard, and Matt Mitchell, who's a recent PhD student of mine. Okay. So the Benjamin-Ono equation is a model for internal waves. So what this means is that, thank you, is that there is a fluid that has two layers. There are different densities of fluid, and there's an interface in between which can move as the different fluid layers are disturbed and they respond due to just gravity. That's the idea. So that surface, that free surface, is called the pycnocline, and it moves around over time. If we allow that surface to move, we can see waves propagating on that free surface, and that's what we mean by internal waves in a fluid. So the Benjamin-Ono equation is one of several famous models for internal waves. It arises in a sort of asymptotic situation of small amplitude waves, very long waves, and also in a situation where one of the fluid layers, the one below in most situations, is infinitely deep. That's the Benjamin-Ono equation, and it's written here. So this function u depends on x and t, and you should think of that as the height of the interface at a position x along a channel, one-dimensional channel, at time t. That's what the u function is. So it looks like a kind of Berger's equation, and then there's a dispersive term that consists of the Hilbert transform acting on the second derivative with respect to x. And in this equation, I'm putting a small parameter in front of that dispersion term because that's what the talk is about. It's about the small dispersion limit, and we're going to make this epsilon become very small and ask what happens to the solutions of this PDE, of this evolution equation. Okay, so right, it's actually not a PDE, is it? Because it's got the Hilbert transform, so it's a non-local equation of some sort. All right. Well, what I want to show you now, I guess we had this all set up so I could show you movies. I got kind of lucky because a couple of, maybe 2 months ago, as it happens, 2025, whoops, sorry, May 16th, 2025, there was an observation of a certain cloud formation over Lake Michigan. And so the idea is that this interface, this pycnocline that's between the fluid layers, if it's in the atmosphere, it can attract cloud moisture. So then you can see where it is. You can see the elevation peaks as sort of locations of the clouds. And as such, if you see some kind of interesting motion of the clouds, you may interpret this as an internal wave. So this is a movie I want to show you of such an internal wave. Let's see. So it's a time-lapse movie. It's not quite this fast in reality, of course, but that's what the cloud motion looks like. It's really it's a soliton is what it is, okay? That's a soliton of the Benjamin-Ono equation moving to the right at some speed like that. So that's the kind of sort of, I guess, phenomena that the Benjamin-Ono equation was designed to model. Okay. So anyway, so what does it mean if this dispersion parameter is small? Well, the logical thing you might say is that the first order, you should just completely set it to 0. Just ignore that dispersion term completely in the PDE. And then you just get, for the same initial condition, you get a simpler PDE, which is here. It's called the Inviscid-Berger's equation. And you know, it's one of the first equations that you study in the theory of nonlinear PDE. It's in Evans' book and every other book. And of course, the fundamental mathematical phenomenon about this equation is that it does not have globally smooth solutions. So you start with very smooth initial data, and then the solution becomes, singular at some finite time, okay, because of what's called a gradient catastrophe. So the solution remains finite, but the derivative becomes like negative infinity at some certain point called the catastrophe point at finite time. So like in this picture, like right down there, this is the catastrophe point. So the x derivative is equal to negative infinity at that point. So you'd have a vertical tangent on the graph of the solution profile. And what that means is that, okay, from this point further on, you have to, decide what this equation would mean, right? And if you look at the textbooks, they tell you you should introduce weak solutions, you should let shock waves propagate, and so on, okay? But that's actually not what happens with the Benjamin-Ono equation. What we're adding is not diffusion, it's some kind of dispersion. And that affects the way that this shock wave in the Inviscid-Burgers approximation gets fixed or regularized over time, okay? So anyway, so this is kind of the picture of what happens if you naively solve the Inviscid-Burgers equation. You, of course, apply the method of characteristics, and that method of characteristics allows you to compute the solution, except that, okay, sometimes there are multiple values, right? In other words, multiple characteristics that hit the same point, and then if you wind the system back in time, you don't know which branch you should follow, right? There's an ambiguity in that multi-valued solution, but still, you can plot it if you want. So like this, at this particular time slice of t equals 3, for some initial data that I didn't draw here, but anyway, it's got multiple bumps on it on the graph. This is the multi-valued solution of the Inviscid-Burgers equation. So sometimes, like in this interval of time, and maybe this interval of space, I'm sorry, and this one over here, there's only one branch. So, okay, very unambiguous solution there. But then this is like the more typical picture. There's 3 branches, there's 3 possible answers, and over here there's 5. So we can kind of subdivide the spatial domain into different intervals where the inviscid approximation, if we allow for this multi-valuedness anyway, has multiple branches, okay? So so this is the idea. There's 2j plus 1 branches, and you can map it out by this integer j that I put on the diagram. Okay. All right, so that's what happens with the approximation. But as we said, when we add this extra term back in to the Benjamin-Ono equation, that's going to have some effect because you see it's got derivatives there, and when the gradients become large, which is just what happens as that catastrophe is about to occur, this term is not small anymore, even though it has a tiny coefficient, right? So you can't toss it out, you have to keep it, and you have to ask what is its effect. And the effect is that it produces what's called a dispersive shock wave, and that's sort of a wave packet of oscillations that have unit amplitude, but very high frequency that's proportional, proportional like 1 over epsilon. Wavelength is like epsilon, okay? So I'm going to show you a movie for this particular initial data, just as a choice. You see half of its graph over here on the right. It's kind of a bump, and so that's the right half of it. It's going to propagate to the right, so I'm only going to show the right half, but you'll see what happens here. So this is the dynamics. So that you see it became very steep momentarily, and then just before that steepness could possibly get to negative infinity, you sort of generate a lot of these peaks that sort of move off to the right. So it looks like an oscillating wave. That's the dispersive shock wave. Okay. Very good. So, so you might look at that picture and say, well, that the dispersive shock wave that got generated, it resembles a train of waves, like maybe a modulated train of waves, a periodic wave, okay? And there's a theory for such things. It goes back to the 60s due to Whittam. And so he developed this theory of wave modulation in lots of different systems. And the basic approach of Whittam's theory was applied in the 1990s to the Benjamin-Ono equation by Dobrokhodov and Krichever. So in that paper, first they derived like the periodic wave solution of the Benjamin-Ono equation, and then they derived what are called multi-phase wave solutions of the Benjamin-Ono equation. So these have like interactions or maybe counter-propagating wave trains that are non-linearly interacting with each other. So they had such a description in their paper, exact solutions. And then they also provided this kind of Whittam theory, the modulation theory of these waves, and describe what happens to the, say, the amplitude of a slowly modulated wave train, what happens to the wavelength of a slowly modulated wave train as this modulation develops, okay? So they wrote some equations down, and they found it's a pretty interesting thing. It's like a hyperbolic system with 2j plus 1 2j plus 1 dependent variables, unknowns. What they found is that they were able to get Riemann invariance for this system, which is really unusual because as soon as you're past 2 fields, you shouldn't expect that at all. There's a geometrical obstruction, but in this case, they found the Riemann invariance, And it was even better than that because the Riemann invariants completely diagonalized the system. It just turned out to be 2j plus 1 independent copies of the same equation, actually, just the inviscid Burger's equation. That's what their sort of formalism predicted, okay? All right. So, well, there's a procedure for studying, initial value problems formally from this perspective. It was developed by Gurevich and Pitaevsky for the KdV equation, the Korteweg-de Vries equation originally. But the idea is that you want to think about an initial value problem with small epsilon, and then how should I sort of model that by patching together modulated waves with some moving interfaces, say, right? And so in 1998, Matsuno wrote a paper studying this kind of Gurevich-Pitaevsky problem for the Benjamin-Ono equation. He took step-like initial data, and he found that the global solution could be described by these J-phase waves, where J is either 0 or 1, okay? So that's like the simplest case. And there was a paper the very next year by Jorge Minzoni and Smythe. They had a more general class of initial data, and correspondingly, they saw more general types of evolution. They were able to see some J equals 2 motions as well. So anyway, it's all very interesting stuff and very compelling. But it has to also be said that these results are formal and they're not attached to a rigorous mathematical description. So we want to know, like, is it true what they're saying, and can we prove it, and can we say more? That's kind of the idea. Okay. All right, so well now, so I want to sort of take a little side trip here and talk about a different equation for a minute. This is the Korteweg-de Vries equation, also with a small dispersion parameter. I put a square on it in this case, but that's how it works. So this is the small dispersion KdV equation, and there's a method to sort of try to study this rigorously. It goes back to Lax and Levermore, 1980s, okay? And so it's based on this idea that the KdV equation is magical. It can be solved by what's called an inverse scattering transform. So there's some kind of nonlinear version of the Fourier transform that you can apply to this PDE and transform the initial data into a scattering domain, a transform domain, in which place the evolution is quite simple, and then you transform back to discover something about the solution of the PDE. That's how it works. And what's true is that when this dispersion coefficient is small, you have a fixed initial condition, that scattering data that's in this so-called inverse scattering transform domain, it depends on this parameter epsilon in a really singular way. And so if you have suitable initial conditions, like you have a smooth positive bump that decays fast to 0, then it turns out that there's an analog of the Fourier transform called the reflection coefficient, and it's negligible when epsilon is very small. But there's also something called discrete spectrum. There are eigenvalues of a Schrodinger operator as it happens, and those discrete eigenvalues obey what's called like a Bohr-Sommerfeld quantization rule in this epsilon goes to 0 limit. See, what really, you should think about like that you have a Schrodinger scattering equation and epsilon is Planck's constant. Okay, so when epsilon is very small, you expect lots of bound states, and that's exactly what happens here. So you follow the Bohr-Sommerfeld quantization rule, and there's some norming constants on the eigenfunctions that you can also approximate. So then what Lax and Levermore did is they said, well, let's go ahead and neglect completely the errors in this direct scattering step in computation of this spectral data. And then if you do that, you just have these point eigenvalues, which are themselves approximations, but nonetheless, you can build the solution that corresponds to those points, and that's called a reflectionless potential in this business, okay? It's what's called an n-soliton solution, and that n is like proportional to 1 over epsilon, okay, which is like the number of points. And there's a determinantal formula in the literature going back to Kay and Moses for the inverse problem for the Schrodinger operator that tells you what this function is as a bunch of determinants, okay? That's the Kay-Moses formula, how to express it in terms of this approximate scattering data that you get up here from Bohr-Sommerfeld. Okay, so yeah, so Kay-Moses tells you that the U, it's the second derivative of some object that you can approximate. This is the Lax-Levermore part now. You can approximate that object by a variational argument and get what's called the Lax-Levermore maximizer. Okay, so you get your hands on this Lax-Levermore maximizer, and then you remember that you had these two derivatives, so you have to take two derivatives of that object, and even though you had strong convergence to this maximizer, the derivatives ruin that, and so you end up in the weak topology. You can prove convergence in the weak topology, but that's the best you can do. So that's what happens in the case of the KdV. That's a rigorous sort of analysis. Now, So what I want to say right now is that the basic ideas of this Lax-Livermore approach could be also applied to the Benjamin-Ono equation. It's just that you have to analyze this sort of n-soliton formula a little bit differently. But let me tell you the answer. It's kind of interesting. I think it goes back to a paper with my former student, Zhengzhe Xu. So suppose you solve the Burger's equation and you just forget about the shock waves and you let the multiple branches appear, okay? So then you can number them. There's U0 is the lowest branch, then U1 and so on. So it's just like this picture. There's U0, U1, U2, U3, U4, for instance, in this interval, okay? So you just put them in order. And then that's solving the inviscid Burger's equation for your chosen initial data. And then uniformly for bounded T, the Benjamin-Ono solution with the dispersion in it there, it satisfies this convergence in the weak topology, the weak L2 topology with respect to the x coordinate, to some function called u bar of xt. And what u bar is just the alternating sum of those branches of the Burger's equation. You just add them up from the bottom to the top with opposite signs, like that, okay? That's how you get the weak limit for the Benjamin-Ono equation. There's a corollary of the proof, not the statement really, that the convergence can be beefed up to strong L2 topology, provided that T is small enough that there's only one branch. So like, if it's blue everywhere in this picture, there's only one branch. So before the breaking time for Burgers, you have this J is 0 everywhere, and then you can actually prove L2 convergence in the strong topology. Okay, so it's kind of a simple answer, and I want to point out that in the KDV case, there's an analog of U bar for KDV. It comes from this variational problem that I was talking about before. And it's really complicated. I mean, all you can say is that you solve this variational problem. You can relate it in some cases to a Riemann-Hilbert problem and so on, but it's not as simple as this, okay? All right. So yeah, so as I said, it's a simpler formula than what you would get for KDV. The same formula has been recently proved by Louise Gassot to be true also in the periodic boundary condition situation. So that's a different version of sort of inverse scattering that you have to use, but she applied it in that periodic case and got the same result at the end. And then even more recently, Patrick Girard, he found a new proof of this weak limit formula that's really by a completely different technique, okay? It's completely different. It has nothing to do with inverse scattering transforms at all. Instead, it has to do with like a beautiful thing, which is a formula that directly writes the solution of the Cauchy problem in terms of the variables x and t and the initial data. It's remarkable. I'll show you later, okay? It's a remarkable formula. But anyway, he used that and he was able to show that this is true in much more generality. So the thing is that all these results have to do with weak convergence in L2 to some object, this U bar function, this one right here. And until now, strong asymptotics have remained elusive. So the thing is, you've got to remember, what is weak topology? You multiply by a test function and integrate, right? And then you take the limit of those integrals and you show that they converge to integration against U bar, right? That's what it is. And that integration has the effect of sort of averaging out oscillations, rapid oscillations, which are obviously present in the solution. You can see it in the plots, right? So you're missing all that. That's what you mean by strong convergence. Find a model for the oscillations so that when you subtract them, you can really prove convergence like in L2 of the difference to 0. That's the idea. Okay. So the rest of the talk is a description of some of the results that we obtained in this kind of direction, as I said, with Elliot and Louise and Patrick and Matt. So, yeah. So the idea here is to capture the actual profile of the oscillations, right? So not so much to enhance them or find a topology where they're dominant, but more to like find the profile and subtract it off so that everything just goes to 0. That's the idea. Get the shape of the waves. Okay. So is this going to work if I? Oh, see, you guys are great. Okay. Let me tell you about our zero dispersion results in this way. So first of all, let's remind ourselves what you do to solve the inviscid Burger's equation by characteristics, right? So you're given a point in the plane xt in the R2 like this, and you look for intercepts y of characteristic lines that pass through the point xt. And you do that by solving this equation here for y, okay? So x and t are given. solve for y. This is the initial condition of your Burger's equation, okay? And then, you know, it's an algebra equation to solve for the y. So for generic points xt and R2, there's going to be like 2j plus 1 simple real solutions, and j is like an integer, okay? So you could put them in order like this. These are the intercepts put in order. And they're all smooth functions whenever this j has an unambiguous value. So if you're not on one of the sort of boundaries of one of these domains, so-called caustic curves, then this has a well-defined value and there's no problem. So anyway, so then the branches of the Burger solution are gotten by just plugging these intercepts into the initial condition function like that. That's how you get them. So that's a little quick review of method of characteristics for this problem. And so there's multiple answers here depending on how many solutions you get of this characteristic equation. Okay. Whoops, wrong direction. Okay. So anyway, so then you can take this thing that you solved for y, and you divide out by the product of all the solutions that you just got your hands on. That's what this is. Okay. And so you're dividing this object that you're setting to 0 by the roots of it, in fact. Okay. And what you get is a quantity that doesn't vanish anywhere because you divided out all the roots, okay? So this g of y is some real valued and positive function of the real variable y, and it behaves like y to the minus 2j at infinity. So that means that you can define this kind of Hilbert transform or something of this g function that we call it capital psi of y. This is a well-defined real valued function. And now we're going to define an approximation of the Benjamin-Ono solution called U0 dispersion, depends on xt and also the parameter epsilon here, in the following way. So first of all, if j is 0, that means that there's only one solution of the characteristic equation, only one branch, okay? So then you just set U0 dispersion to be that Burger solution. No question about that, okay? The issue is, what do you do if you have multiple branches? Let's see, this way. No, wrong way. Okay, I'm going to do that several times just so you know. So otherwise, if you have multiple answers, then you let h of y denote the thing you would study in diffusive shock waves. The Lax-Olenek objective function is this thing. You try to minimize that if you're solving for like the shock wave position in the classical theory. But anyway, so you have this function, and the critical points of this thing are exactly the intercepts yk of the characteristic lines. Okay. So usually what you do in shockwave theory is you try to pick the correct characteristic, and that's a minimization problem, right? So that's the idea. But here, we're going to need all of the characteristics. Okay, so then we define some nonlinear phases, j of them, in this way, just by taking the difference at consecutive critical points of this function h up here. Those are functions theta j of xt. And then there's some corrections to those phases that are built from that capital psi function that we had on the last slide. Okay, again, evaluated at consecutive critical points, okay? And then I'm going to build a quantity gamma j, whose modulus is going to be shown on the next slide, but it has the phase of this slow correction, this phase correction phi j, okay? So the modulus of the gamma j is, okay. The modulus of gamma j is the square root of this expression on the right-hand side, and what it is it's just built up out of those Burger's branches, okay? Products of differences of the Burger's branches, but it's an explicit formula. This right-hand side is always positive, so there's no problem defining the square root of it as a positive quantity. That's the modulus of the gamma j. Okay, so now we're going to build a matrix M out of all this stuff. It's a j by j matrix with elements written here. So there's some diagonal part that's just got those gamma j's, and then these fast phases, they're divided by epsilon. It makes them fast or rapidly oscillating phase factors. And then there's an off-diagonal part. Well, actually, it's not always off-diagonal, but anyway, this rest of the matrix, let us say, that is just built out of the Burger's branches in this way. So j and k are the indices of the matrix, right? So we have this matrix M now, okay? And then finally, what we're going to do is build the zero dispersion formula for these j's bigger than 0 in this way. So there's a part of it that involves just the Burger's branches, okay? Just the sums of the Burger's branches. And there's another part, has 2 times epsilon imaginary part of the derivative of log of det m. So determinant of m, that's the matrix we just built. So what one can check, okay, one can check from this, from the definition of the thetas, that if you differentiate them with respect to x, these fast phases, then you get just the difference of consecutive Burgers branches like that. And if you take minus the t derivative, you get the difference of the squares of the Burgers branches, okay? And so one thing that this tells you is that if there's no modulation, if these Burgers branches are all just numerical constants, uj, okay? So in that case, the phases are all linear functions, and this U0 dispersion formula turns out to be exactly the same thing that Dobrokhotov and Trichever wrote in their 1991 paper for a multi-phase wave solution of the Benjamin-Ono equation. So somehow this is it's like a multi-phase wave, but it has this extra modulation because these are not constants anymore. That's the thing, okay? Okay. All right, so the first sort of rigorous result obtained by this new methodology is this one that came out last year on arXiv. So suppose you take an L2 initial condition and suppose it's a rational function with simple poles, okay? The poles are, of course, in the complex plane. It's an L2. So let U of xt epsilon be the solution of Benjamin-Ono with the initial condition U naught. So then as long as you consider points xt in the plane for which this Laxalanic objective function has only simple critical points, now we're allowing possibility of complex critical points. They also have to be simple, but that's a generic condition, okay? So then you can write that the Benjamin-Ono solution is equal to this thing we just built, this U0 dispersion function, plus order epsilon. And this order epsilon is something that's holding pointwise in xt, but also locally uniformly. So as long as you stay away from these sort of exceptional curves in the space-time where there's like a double critical point of the h function, as long as you stay away from those, there's no problem. Okay. So a corollary under the same conditions, if t is such that there's sort of, either no phase or there's a single phase oscillation. That's what this means here, okay, for generic x that are on the real line, then the convergence is actually happening in this sort of different sense in the L2. So you subtract the zero dispersion profile, you take the limit in L2, it goes to 0. That's what we're talking about, right? So yeah. Yeah, so jxt equals 1, you're beyond the shock and you have a periodic wave. You have a modulated single phase periodic wave.
But so this is for the shock formation.
Right. Yeah. So and even beyond that, this theorem is true even if that breaks down into multiple phase waves. So the zero dispersion profile works. I'll show you a picture in a second, but it works even beyond that. But this is a technicality, I'm pretty sure that you can prove this another way, even more generally. But for now, let's just say that. Yeah. So this is a picture of the zero dispersion profile, kind of plotted, in a density plot or whatever over the xt plane, along with these are the curves. This kind of star-shaped picture were the curves we had in the first part of the talk. It's where the Burgers solution doesn't know how many branches it has because you're at sort of you're at a boundary point, okay? So these are like the so-called caustic curves for the Burgers problem. But in between the caustics, everywhere you get locally uniform convergence to this crazy profile. And as you can see, like in this region in between, there's a kind of counter-propagating wave profile. I don't know how else to describe it really, but that's what's going on, okay? So that's the solution. Okay. Right, so now I want to talk about, what's going on near these boundary curves. So the earliest time, we call it t critical positive, for which there exists an x critical with a negative infinity derivative. That's called the gradient catastrophe point for the inviscid Burgers equation, and it's right here. This is xctc is right there, okay, for this problem. And so what happens is that for t bigger than the critical time, there's locally two curves. You see them here. This is x equals x minus of t. This is x equals x plus of t, okay? And for a given dispersive regularization of the inviscid Burgers equation, like KdV or Benjamin-Ono, in between these two, there's a dispersive shock wave, okay? That's the idea. So we may ask questions then about what's going on here. So it's of some interest to determine how a given dispersive regularization of the inviscid Burgers equation behaves near these x plus and x minus curves, including, by the way, close to the intersection point, that critical point, okay? So in the next part of the talk, what I'm going to do is sort of show you the answers to these questions for both the KDV and the Benjamin-Ono cases, and we can then compare, contrast, and discuss, right? That's the idea. So the first thing to do is to describe these curves themselves, because they are not the same thing for the two equations that we're talking about here. So for KDV, you get your hands on these x plus and x minus of t curves by looking at what's called the 3x3 hyperbolic Witten system, which governs like the periodic, modulated periodic waves for Benjamin-Ono. System has some degeneration, and the degeneration locus for that system is a system of two curves, x plus of t and x minus of t. That's how you find the answer for KDV. It's quite complicated, really, but it can be done. However, for Benjamin-Ono, the answer is a lot easier. In fact, we already talked about it. What they really are just the caustic curves for the inviscid Burgers equation. In other words, the curves in the xt plane where you have ambiguity as to how many branches of the solution you actually have, okay? So that's what's happening there. Okay. All right, so now the edge, the x equals x minus of t, we call that the harmonic edge of the problem. The reason we call it that in both cases is that, well, the amplitude of the dispersive shock wave goes to 0 at the left edge. That means that the equation becomes almost linear, if you like, at the left edge as a perturbation of the background, and therefore you expect sinusoidal waves, right? Something sort of sinusoidal. So that's called the harmonic edge, okay? So for KDV, one thing is that if you look at the small dispersion profile coming out of, like, you know, some kind of variance of this Lax-Levermore stuff that's been beefed up to capture the strong asymptotics, you discover that the amplitude of the oscillations goes down like a square root at the edge of the zone, okay? Right as you approach that dispersive, that harmonic edge, square root amplitude. But for Benjamin-Ono, when you redo the calculation using the formulas that I just discussed, you get 1/4 root instead. So it's a much kind of sharper jump down to 0 amplitude for Benjamin-Ono than for KDV. But you still may wonder, how does the dispersive solution behave close to this harmonic edge? Okay, so first let me tell you about the KDV problem. So if we answer this question for KDV, we have to describe what's happening using a certain kind of nonlinear special function, okay? So this is the so-called homogeneous Painlevé-2 equation right here. It's a cubically nonlinear and non-constant coefficient second order ordinary differential equation for Q of x, okay? So this equation has a special solution called the Hastings-McLeod solution. We'll call it QHM of x, that has the property that as x goes to positive infinity, it behaves like the Airy function. It decays. So if Q decays, you might neglect the Q cubed term, and then you see Airy's equation there. So it's logical maybe to expect that you should see some multiple of Airy. If the multiple is 1, then that's called the Hastings-McLeod solution, okay? So as x goes to plus infinity, that's how it behaves. And then by some miracles, it's known that in the opposite limit, as x goes to negative infinity, the same solution behaves very differently. It looks instead like a square root, which is like the balance between these two terms in the equation, okay? So that's what's happening in the opposite direction. And the fact that it's known that going from here to here, you can write both of these formulas consistently, that's what's called a connection formula in the theory of Painlevé equations. It's a big deal that we can do that. So anyway, so that's the Hastings-McLeod solution. It kind of looks like a square root in the left-hand direction. It's over here. And in the right-hand direction, it decays like an Airy function. Okay. So then here's the result for KDV. So first of all, at the harmonic edge, okay, there's sort of a phenomenon by which the solution becomes sort of linear, as I said. So the oscillations, which are nonlinear things, are actually described by some elliptic functions in the KDV case. Those elliptic functions have to turn into trigonometric functions, which means the elliptic modulus goes to 0, okay? So m goes to 0, that's the modulus of the functions. And so what's happening is if we look near that left edge for KDV, we're going to define u minus of t to be the restriction of the Burgers solution coming from the left. That makes total sense to approach from the left and define this limiting value. We'll call that u minus of t. And now u of xt epsilon is the solution of the KDV equation with u naught initial beta. So here's the theorem of Tom Kleiss and Tamara Grava from 2010. So we fix a time bigger than the critical time. So then there exists a positive function w, a positive function k of t, and then a phase, theta 0, which is affine linear in x minus the edge, okay? such that the KdV solution is equal to that Berger's solution coming from the left, and then minus epsilon to the third amplitude W of t times this QHM of negative x, and then there's a cosine plus small, epsilon to the 2/3. So this cosine, that's the harmonic edge part talking, right? It's like a sinusoidal oscillation. But the thing is that the amplitude of that cosine is really governed as a function of x by this thing right here. This is the Hastings-McLeod solution, okay? So what we're saying is that the amplitude profile of the dispersive shock wave for KdV near the edge, it looks like this Hastings-McLeod solution, okay? So that's what's happening here. It's described by QHM of minus argument. Okay, so that's the KdV case. So now what about Benjamin-Ono? For Benjamin-Ono, the harmonic edge, as we said, it's a different curve, but still you could evaluate the Berger's solution on that curve. And now we're going to let uxt epsilon be the solution of Benjamin-Ono with initial data u0, which we'll take to be a rational function with simple poles. Okay, so there's only simple non-real critical points at xctc. Okay, so then the theorem is the following. So suppose we fix a time that's a little bit north of the critical time. So then again, there's some positive functions w and k. There's also a real valued function beta and a affine linear phase theta. By the way, I'm saying there exist these things, but actually there are formulas for them. I just don't want to put them on the slide, so just so you know. Anyway, so that the Benjamin-Ono solution is the Berger's solution plus epsilon to the 1/6 times amplitude. And now here we have real part of, okay, again, the phase oscillation. It looks like the cosine term, but divided by area of e to the minus I pi over 3x plus small, order epsilon to the third. Okay, so how do you read this? Well, as we said, the real part of a phase should somehow be like the cosine, but the area function has also some phase, so it's a kind of modulation maybe of the cosine, a mixture of sine and cosine if you like, but still, it's a sinusoidal oscillation. And the amplitude here is what you get by just putting this area function in the denominator with absolute values on it like that. So this is like the Benjamin-Ono version of the Hastings-McLeod solution from KdV, I would say, okay? That's the way to think about this. Okay, so here's some graphs just to convince you of it. So, so the approximation is the black curves in all the cases. So epsilon is going down 2 to the minus 6, 2 to the minus 7, 8, 9, and so on. And then the red curve is the actual solution of the Benjamin-Ono equation. And you can see that the convergence is getting better the smaller the epsilon is getting, even though there's more and more oscillations inside of the packet, okay? So that's the idea. Okay. So if we want to make a comparison here, we can think about like the fluctuation, the amplitude fluctuation, or the width, if you like, of the perturbation from the background at the edge. So in the case of KdV, the amplitude fluctuation is like epsilon to the third, whereas for Benjamin-Ono, it's bigger. It's epsilon to the power 1/6, right? And the width in both cases is similar. It's like epsilon to the 2/3, okay? So the zone is the same width, but the amplitude is bigger for Benjamin-Ono than for KdV. For both cases, the formulas are sensible. In the case of the KdV, the reason is that this Hastings-McLeod solution is known to be a global real valued solution of Hamlet A2, so it doesn't have any singularities. It makes sense for every x. And for Benjamin-Ono, it's a property of this area function. Now, this is not the area function on the real line because e to the minus I pi over 3, so you're slicing the complex plane. It's a angle, but you look at that area function on that angle, there are no zeros there. It's well known that the zeros of the area function are all negative real numbers, so no problem there. Okay. And moreover, as x goes to plus or minus infinity, this KdV formula, also the Benjamin-Ono formulas, they match onto the asymptotes that we already know from the sort of the behavior away from the harmonic edge, I would say. So for KdV, the amplitude grows like a square root going away from the center. That's because the Hastings-McLeod solution behaves like a square root. And so that's matching exactly what we expected. For Benjamin-Ono, we expected 1/4 power, and that's coming from the area function again, because if you expand this thing out as x goes to plus infinity, you pick up at x to the power 1/4 from the area asymptotic. So it's coming out from there. Okay. So then there's the other side of the picture, the other side of the shock wave. That's called the soliton edge. Okay. What's happening there is that in both cases, the wavelength is going to infinity for this oscillation. In other words, you're getting isolated peaks as opposed to a periodic traveling wave in the limit. Okay. as x goes up to x plus. So those peaks are called the solitons of the PDE, and so we call it the soliton edge. In both models, the fastest solitons are also the tallest ones, so they come out on the right-hand side, and they correspond in both cases to the most negative eigenvalues of the corresponding scattering transforms. Okay, so for KdV, we had this Bohr-Sommerfeld quantization rule, and if you look carefully at that rule, you see that there's actually a finite density of the most extreme eigenvalues. But for Benjamin-Ono, it's a different scattering problem, and what takes the place of Bohr-Sommerfeld is something called the Weyl density, I guess, is what's called Matsuno's density formula. And this thing actually vanishes at the most extreme eigenvalues. So what it means is that you should expect there to be fewer solitons with extreme amplitudes or extreme speeds, I should say, compared to KdV. But how is this all quantified rigorously? So let's take a look at the results here. So first of all, for KdV, so at the soliton edge, those elliptic functions that we were talking about before, they degenerate in the other direction. Now they turn into hyperbolic functions instead of trigonometric. So you get like, hyperbolic secant squared is what you're looking at. Actually, that's the profile of the KdV soliton. That's what emerges from that kind of limit process. And so if we let u plus of t be the Berger's solution continued from the right now up to the edge curve, the soliton edge curve, then with the solution u xt epsilon of KdV, Kleist and Grava proved the following the next year. So if we fix a time bigger than the critical time, there's a speed function c of t positive, a real function r of t, so that when epsilon is going to 0, the solution of KdV is the Berger's solution plus this kind of arbitrary finite sum, okay, 1 to capital M, of solitons of the KdV solution, but evaluated at some argument like this. So there's log of 1 over epsilon, square root of c is just the speed parameter, that's natural, and then x minus some center position, an of t and epsilon, plus an error term that's proportional to epsilon log epsilon to the power 2. Okay, so this formula holds uniformly as long as this capital X variable, which is basically x minus edge divided by epsilon log epsilon, is bounded. And provided you choose this m to be sufficiently large compared to your bound on that quantity, okay? And here, these ANs, okay, these are the centers of the solitons. They're basically equally spaced, like n minus a half there, n plus a half there. And then there's this term, which is a correction. It's got 1 over log, that's something small. And then there's these quantities that involve these are actually the norming constants of the Hermite polynomials, if you know something about that. That's what those things are. But actually, these numbers, you see, they go to 0 super fast because this n factorial square root in the denominator like that. And that's maybe a problem. You're taking the log of such a thing and make compete with this quantity, right? So that's something to keep in mind. Okay, what about for Benjamin-Ono? So again, x plus is a different curve in the Benjamin-Ono case from KdV, but we can still evaluate the Berger's solution from the right on that new curve and call that thing u plus. So now we're taking the u function to be the solution of Benjamin-Ono for this kind of simple pole rational initial data, again, of the same sort we had before. And now we're going to be using Benjamin-Ono solitons in this problem. So that's a different formula. The Benjamin-Ono solitons are rational functions of this sort. So this is like a Lorentzian profile, and c is the speed parameter. So it's like the amplitude of the wave is this parameter c, and also its speed. Okay, so here's our theorem in this case. So we again fix a time a little bit bigger than the critical time. There's a positive speed function, a positive function k of t, and a real valued function we call gamma of t, such that for small epsilon, the Benjamin-Ono solution is this Berger's part, plus, now look at this, it's an infinite sum, now instead of a finite sum, of these Lorentzian soliton profiles, okay? Also with a scale, this time it's epsilon to the minus 1/3 coming there instead of this log term that we had before, and x soliton minus some an here. What is this an? Those are the zeros of the Airy function, actually. Okay, so I'd like to talk about these formulas a little bit. First, I'll show you pictures. So these are this is the sort of comparing the actual solution red of the Benjamin-Ono equation with this approximate formula, this infinite sum of soliton peaks. epsilon 2 to the minus 6 through 2 to the minus 9. And you see that the convergence is improving, as you would expect, when the epsilon is getting smaller and smaller. And here I just highlighted these are the Airy zeros, so you see that the peaks are really showing up exactly at those points. Okay. All right. So yeah, so what if we compare these formulas? In both cases, the formula is a sum of identical exact soliton solutions that are propagating on this constant background U+. But a couple differences. So in KdV, the spacing of the solitons has this log in it. So it's proportional to epsilon log 1 over epsilon. And that's only a hair bigger than the actual width of the solitons themselves, proportional to epsilon, okay? Log is almost nothing, right? So they're separated, but they're just barely separated from each other in some way. Whereas for Benjamin-Ono, the spacing is epsilon to the third, and again, the width is epsilon. So that's a much bigger gap. Okay, so the solitons for Benjamin-Ono really are more dilute at the front edge than the ones for KdV, and this is the reason why, actually, okay? This is the reason why. But there's more. For KdV, the solitons that make up the wave train, they're equally spaced at the leading order because the spacing had to do with this n plus a half factor times epsilon log epsilon. But for Benjamin-Ono, they're not equally spaced. Instead, they follow the zeros of the Airy function. They sit at those Airy zeros, okay? So you might think that maybe there's a way to compute the zeros of the Airy function by a physical experiment, like you observe the waves as clouds in the sky, and then you look at these clouds and you could determine from them where the zeros of the Airy function are. But that's probably just dreaming, right? Okay. Well, some more. In both cases, there's also an effect where the deeper that you look into the dispersive shock wave, the more dense this train of solitons becomes. You're moving away from that sort of rarefied edge in both cases. And the mechanism in the KdV case for this is those Hermite constants, the log of those HNs, which remember they had this square root of n factorial in the denominator. They're getting super small, right? And since the logs go to minus infinity faster than minus n, what it means is you could really, that's why we have to truncate this formula at a finite sum of solitons, because eventually, if you let the n get big enough, the solitons start going backwards and they will run out the front of the dispersive shock wave. So it's going to pull them on the opposite side. So that's why you have to truncate the sum. But anyway, in the Benjamin-Ono case, the same kind of thing is achieved by a different mechanism. Instead, it's just due to the Airy zeros, which, as you know, they become more dense, I guess. The distance between them gets smaller and smaller the further out you go. So that's the reason why it happens in the Benjamin-Ono case. So because they form an infinite decreasing sequence, we really can use an infinite series in the case of the Benjamin-Ono problem. We can't do that for KdV for this reason that I explained. Okay. All right, so the last part has to do with the gradient catastrophe point itself, XCTC. That's really the same point in the space-time plane for both equations. So there's reason to believe that the dispersive solution might even behave in a more universal way. So maybe it's not only the case that the dispersive shock wave that's forming is independent of initial data, modulos on the scalings anyway, but actually there was a thought that maybe it shouldn't even depend on the equation that you're using. The form of the dispersion. This is a conjecture of Boris Dubrovin from 2006. He said there should be a universality class of dispersive Hamiltonian perturbations of the inviscid Burgers equation for which the solution near the shock point for the Burgers problem can be scaled regardless of initial data and regardless of the equation in the universality class to match a certain canonical function d of xt. I'm going to call it that for Dubrovin. What it is, it's a special function that solves the second equation in the Painlevé-1 hierarchy. And this conjecture was suggested by some matched asymptotics and canonical perturbation theory and so on. That's the idea. So, the function d in Dubrovin's theory, it satisfies an ODE. This is a fourth order ordinary differential equation in X in which the t, which is an argument of d, just shows up as a parameter in the ODE right there, okay? So it's a constant, really. You solve this fourth order nonlinear and non-constant coefficient ODE, non-constant because of this x over here. And that's what gives you the d function, provided that you put the right boundary conditions down. And those should be like cube root behavior as x goes to plus or minus infinity. And this equation is the second equation in the Painlevé-1 hierarchy. Okay. So that's the object that we need for that theory. And okay, and then to go further, the KdV equation definitely is a member of de Brovin's universality class, but it turns out the Benjamin-Ono equation doesn't fit into that class. Instead, there's a corresponding conjecture about the Benjamin-Ono universality class that appeared in this paper, 2015. So there's a universality class of dispersive Hamiltonian and non-local perturbations of the inviscid Burgers equation, for which the solution near the critical point can be scaled independent of initial data and independent of the equation in the class. To match another thing, we'll call it capital U of xt, which should be a particular special function that solves this equation. They call it a string equation in the paper. It's some kind of non-local, because of Hilbert transform, version of that de Brovin equation, right, of that P12 equation. And again, you should look for the solution with cube root asymptotics for large x. So that was a conjecture in this paper. So, turns out that de Brovin's conjecture is true for the KdV equation, and this was proved in a third paper of Kleis and Grava in 2009. So UC is the U value at XCTC for the breaking Burgers solution at the gradient catastrophe point. Initial data is U0, and you make a constant K out of the third derivative of the inverse function of U0 evaluated at the critical value like that. So, okay, so then you have a moving frame, x minus x critical minus 2 Burgers speed UC t minus t critical divided by epsilon to the 6/7. That's your x coordinate, and t is a scaled version of t minus tc by epsilon to the 4/7. So if you fix those variables, then the solution of the KdV problem converges in this way. So uxt is the critical value plus some constant, which is proportional to epsilon to the 2/7 times de Brovin's function, plus order epsilon to the 4/7 as epsilon goes to 0. So that's the universality result in the KdV case. It's been proven now. So now I would like to talk about the Benjamin-Ono case. So suppose that u of xt is defined now by an explicit formula. I'm not going to write the equation here. I'm writing a formula for it. So u of xt is minus 2 imaginary part d by dx of log tau. And tau is a Pearcey integral. So here's the quartic exponent, and the contour of integration, gamma, in the zeta plane is like an elbow shape that goes from this direction at infinity to this direction. So it's turning by 90 degrees. So then numerics suggest, from computations anyway, that this quantity does not vanish for any real xt, but actually we don't have a proof of that. So if you have any ideas, I would love to hear them from you. But anyway, that's a quantity that I'm going to put into this formula here. Okay, so then here's the theorem. So suppose that U0 is an L2 simple pole rational initial condition. This H function should have only simple non-real critical points at the catastrophe point. And XCTC-UC is a generic gradient catastrophe point for the inviscid Burgers equation. So, we define a constant K from the third derivative of the initial data like this at the critical intercept value. And then the solution of Benjamin-Ono is equal to the critical value plus epsilon to the quarter over K times U of xt plus order epsilon to the half as epsilon goes to 0. And this is uniform for xt in the plane in compact sets on which this tau function is non-vanishing. So that's that integral that I was worried about before. So as long as that's non-vanishing, then you have this on compact sets. And here the coordinates are again related to a sort of Burgers translated frame of reference, but divided by epsilon to the 3/4 here. And for t, it's epsilon to the 1/2, just like that. So it's a simpler formula, I have to say. So here's some pictures of it. Actually, steepest descent analysis shows that this u function really does look like a cube root at infinity. And here's some plots for different values of t. So you see that it starts to grow these oscillations just as you might hope for. And then this plot is just illustrating, again, the convergence on the x scale. This is the capital X coordinate. So epsilon equals 0 here is the limiting solution that comes from the u. That's this thing with the dotted line. And then you see that as epsilon gets smaller and smaller, you're moving right up to that curve. So, okay, so one thing we don't yet have a proof of is that this Pearcey u function, the log, imaginary part of the log derivative of this tau, solves this string equation that was in the paper of Mazzuero, Raimondo, and Antunes. But we did do numerics, and it really is true. So we just need a proof of that. Okay. Okay, so now I want to tell you how we get these results quickly, just flash some formulas. So I told you I would show you Patrick's amazing formula, and here it is. This is how you solve the initial value problem for Benjamin-Ono in Patrick's paper. So first of all, you see that there's like the resolvent of some crazy linear operator acting on pi u0. So pi is some operator which is the orthogonal projection from L2 onto the Hardy space of functions analytic in the upper half plane, right? That's what that is. So you act on that thing with this inverse function of the inverse operator, and then you evaluate a functional called I plus. It's just the limit from the right of the Fourier transform, okay? So anyway, that's the formula of Patrick's. And I will just show you the result because I'm running out of time. So, to describe our result, what we have to do, let me go back, I think. Yeah, okay, so just to remember what we had this initial condition that was a rational function with simple poles, so we'll write it this way. These p's are in the complex plane now, and the c's are the coefficients. And so then we put in the antiderivative of this u naught into the Lax-Alainic objective function, and the critical points satisfy this equation, which is exactly what we expect. But you see there's logs here, so we're going to need some branch cuts to understand this, and we put them on the picture like this. It's a crazy picture, but the important thing is that they all come out of the poles and they go off in the northwest direction. That's the important feature of this picture to notice, okay? So we have that, and then we have to introduce some contours of integration that relate to those cuts. So here's a picture of the contours. Basically, they're encircling the cuts, okay? One for the first one, the first two cuts for the second, and so on. There's an exceptional case that I'm not going to talk about now, but that's the only thing. So we have some contours. And now we build two matrices of size n plus 1 by n plus 1, A and B. And A and B are exactly the same except for the first column, okay? And in each case, the integration is the same in each row. So we have, maybe I didn't show you the pictures. Did I show you the contour pictures? Yes, I did. So there's this C0, which is kind of diagonal like this, and then the other C's are wrapping around the branch cuts, okay? So anyway, in each row, we're integrating on the same contour in the complex plane, and in each column, it's the same integrand, okay? And the integrands are even the same for the A and B matrices, except in the first column. So in the first column for A, we have the initial condition u naught. In the first column for B, we put the function 1, and always multiply by this e to the minus I h over epsilon, okay? So at this point, we have two matrices of size n plus 1 by n plus 1 made of contour integrals. And here's the theorem, is that the solution of the Cauchy problem for Benjamin-Ono with that rational initial condition is just twice the real part of det A over det B. That's it. And you can write the formula in a different way, but I'll just skip that for now. So that means that the whole problem of analysis of these solutions boils down to looking at contour integrals that have small denominators in the exponents. So classical steepest descent method. And I'll skip this part just to show you what's going on. So yeah, so all of our theorems are proved in the same way through that classical steepest descent method. As long as you stay away from those Berger's wave caustic curves, the critical points of H are all simple points. And so the standard steepest descent formula for saddle points works, and you just use that. But if you're close to one of those curves, now you have a situation where you've got like two critical points that are very close, and you have to deal with that. Right? Or three, actually, at the critical point. So the pictures kind of look like this. So at the harmonic edge, there's like a simple critical point over here, and then there's a double critical point, or something close to that, over at this point. And so what's going on there is that you've got to thread the contours around that double critical point in such a way, when you use sort of normal forms to analyze things there, you pick up an exponent that's got a cubic in it. And that's exactly where the Airy functions come from in this problem. Similar thing is happening at the soliton edge. But near the gradient catastrophe point, three critical points are all colliding at xc, like this. And so you get a quartic exponent as the normal form, and the contours look sort of like this. And that's really where this Pearcey integral is coming from. Okay, so that's some pictures of these morning glory clouds from Michigan. Thanks for your attention.
We have time for maybe one or two quick questions.
So I remember that for the Clay-Scravers result, when the initial condition is generic, then they prove the Dobrovin's conjecture. But when the initial condition is non-generic, is specially chosen, then they can show that the limit, the small dispersion limit, is not the the P12 limit, but some higher numbers in a hierarchy. So
yes.
in your result, in the generic situation, you find that the limit is Pearson integral like so function. Then if similarly, if the initial condition is not so generic but specially chosen, then do you have a hierarchy of limits? And if you have, then which hierarchy?
So I expect that the answer is yes. The details are yet to be worked out, but you see what's going on. The reason that you get the Pearson integral is because there are three critical points, three simple critical points that coalesce, right? So if you had the next order, you would have 5. It would be the next typical coalescence. And then you would have to use like an exponent with a sextic polynomial instead of a quartic, and you'd have a natural, what are they called, diffraction integral that you would have to use, or a catastrophe integral to give the correct kernel in that case. That's what you're asking about?
Yes, I would expect some hierarchy.
Well, here in Benjamin-Ono, it looks like you don't ever get Hanleve equations at all. That's the thing. You just get nonlinear expressions, explicit nonlinear expressions in classical special functions. That's maybe the message.
All right. I think we should take time for a quick coffee break. Let's thank Peter again. And we'll continue in 12 minutes.